Hello students, in today's video we're going to work on integral as net change. So we're going to practice applying our integrals, definite integrals, to application problems. So let's get started. So find the total area between the x-axis and the graph of y equals x squared minus 1 from 0 to 2. So what I wanted to do is pull up that graph and give you a better idea of what that looks like. Now in this graph you'll notice, so I'm going to zoom in and make it easier to see, that if we find the area between the curve from 0 to 2, we're really finding the area from here to here and the area from here to here because it says between the curve and the x-axis. So this is the areas that we'll receive. Now if we take a look at both of those, we're going to get something different. Now if we take the derivative for the from 0 to 1, and in the interest of time I'm doing this on my calculator, if we find the area from 0 to 1, we get negative 0.667. So this gives us negative 2/3. Now if we do it from 1 to 2, we get 1.33 or 4/3. Now because we're trying to find the area between it, we need to make sure that this 2/3 listed down here becomes positive because we're trying to find the area between the curves. So what we're going to end up with is 2/3 plus 4/3, which is equal to 6/3, or 2. So we know the area between the graph and the x-axis is going to be equal to 2. Now if you do this on your calculator, you want to separate these based off of when the graph or your area would go from negative to positive. Another way to do this is, remember, if you take the integral of the absolute value of the function, that'll also yield the same result as what we did here by hand. But I wanted you to see how this is affected because I know we haven't done it in a little bit. So let's take a look at another piece here. Now remember, we're going over integrals as net change. So a couple things we also need to talk about is displacement. Now displacement talks about your final position minus your initial position. So this just talks about where we are, not how far you've gone, but literally where you are located. So the displacement is equal to s of t minus s of 0. Your displacement can also be written down as the integral from 0 to t for v of u du. Because remember, the antiderivative of velocity is displacement, and then the derivative of displacement is velocity, and the derivative of velocity is acceleration. So now when we're trying to find the distance traveled, we want to add the motion in all directions. Now to do that, just like when we found the total area, we want to do the distance traveled is equal to the antiderivative from 0 to t, the integral of 0 to t, for the absolute value of v of u du. So this is the same as finding the total area between a curve and the x-axis, just like we did in the warm-up. Now, let's look at this problem together. It says v of t is equal to 6 of t minus 18t plus 12 from 0 to 12. In this particular case, it talks about a particle that's moving along the x-axis with a velocity of v of t in meters per second. So they want us to A, determine when the particle is moving to the right, to the left, and when it's stopped. Also, we want to find the particle's displacement for the given time interval. So remember, this is talking about where they are located, not how far they've traveled. And finally, we want to find the total distance traveled by the particle. So let's take a look at the graph because I really want to make sure you understand what this looks like graphically. So here we have this image. And remember, we're trying to find the area, or we're trying to find a number of things. So let's pull this up so you can see the entire graph. So what we're doing here is we are trying to find that area. We're trying to find the displacement. Now, you'll know if you did this in your calculator, it would show you these specific portions for you. Notice that it hits the graph here at 1, and then it starts to go under. So what I want to make sure of first is we understand what's going on here. Now, you'll notice, and I'm going to do this in blue, from 0 to 1, the velocity is a positive number. It is decreasing, as in like we're slowing down, we're slowing down, we're slowing down, because you'll notice the velocity is 6 and it goes down towards 0. As soon as we hit the 1 second mark, you'll notice here that it's now 0. That means this is when it stopped. So when our velocity is positive but slowing down, that's when we're going to the right. And then when we hit 1 second, we're stopped because you'll notice the velocity, it says 0. Moving forward, when we get past 1, you'll notice our velocity is negative. That velocity, we can't have a negative velocity. You can't go a negative speed. What it does mean, however, is that you're moving to the left because the velocity is going backwards. It's almost like you're going in reverse. And you'll notice here at 2 seconds, we're at 0 again, which means that is when the particles stop moving. So to recap, moving to the left from 0 to 1 second, moving to the right, moving to the left, moving to the right from 0 to 1 second, moving to the left is going to be from 0 or 1 to 2. Notice I didn't include either one. Particle stopped at t equals 1 and t equals 2. So that's going to be when our graph is moving right, left, and stopped. So let's take a look at the next question again. It says find the particle's displacement for the given time interval. So to look at that, what I didn't give you is this initial value. So this is something I forgot to give you. So I'm going to write it down now. S of 0 is equal to 3. So going back to our formula, displacement equals initial displacement. I'm going to go back just to make sure you see it. It's going to be our final position minus our initial position, or it's going to be the displacement located on the bottom, the integral from 0 to t for v of u du. Now, what I didn't tell you is that S of 0 is equal to 3. That means at 0 seconds we started off at 3 meters. So what we're going to do now is we are going to integrate from 0 to 2 for our function v of t. And to save you some time, I've done that work for you. It turns out to be equal to 4. So our displacement is going to be equal to our initial displacement plus our final displacement. Because notice we started at 3. That means we were 3 ahead already. And now we're going to go an additional 4. Now notice that when we integrated from 0 to 2, we took into account how much we moved left and how much we moved right. That's why we don't need to do the subtraction like you saw in the formula listed. So we're going to move on, and I'm sure you'll ask me questions when I see you in class again. So the distance traveled, we talked about. One more, this is actually a really easy problem. The rate at which your home consumes electricity is measured in kilowatt hours, or kilowatts. If your home consumes electricity at a rate of 1 kilowatt for 1 hour, you will be charged for 1 kilowatt hour of electricity. Suppose that the average consumption rate for a certain home is modeled by the function C of t equals, you could read the rest, where C of t is measured in kilowatts and t is the number of hours past midnight. So it's really important to read that. And it says find the average daily consumption for this home measured in kilowatt hours. So we are literally taking the integral for C of t from 0 hours past midnight to 24 hours past midnight. And when you punch this into your calculator, make sure one, your answer, your mode is in radians if you're going to do it the graphing route, because we want to make sure that because they're using pi, they're using radians. And when you do that, your answer turns out to be 93.6 kilowatt hours per hour. Or actually kilowatt hours because they said in an average daily. So 93.6 kilowatt hours per day. So that's all for now. I'll see you guys next time.